Lesson 9.6, Applications of Matrices. One application of matrices is Cramer's rule, which is used to solve a system of equations. It's just ratios of determinants. So your first variable is the determinant of A1 over the determinant of your matrix. A is the coefficient matrix, and AN is the coefficient matrix with the column n replaced with the constants. See what I mean in a minute. If the determinant of the coefficient matrix is 0, then there is no solution or many solutions, and you don't know which, so you'll have to solve some other way to figure that out. All right, let's solve using Cramer's rule. So to find x, the bottom is the determinant of the coefficients. The top is the coefficients, but the column you want to solve for is the constant. So in this case, I'm solving for x. So my first column is the constants. The other columns are still the coefficients. So it's just a matter of finding these two determinants. So let's use the shortcut of copying the first two columns. So that's 12 plus -9 plus 1 minus, since I'm going up, 3 minus 18 minus -2. Repeat for the bottom. -4, +4, plus 0 plus -1 minus 0 minus 6 minus 2. Put those together, add up the top, I get 15. Add up the bottom, I get -5. 15 over -5 is 3. X is 3, and that's the really cool thing about Cramer's rule, is you can solve for one of the variables without having to solve for the other variables. Of course, this problem wants us to solve for the others, so let's go ahead and solve for y. The top, the y column, the second column, is the constants. All the other columns are still the coefficients. So it's the coefficients of x, the coefficients of z. And now the bottom is just the determinant of the matrix of the coefficients. Well, we already figured that out was -5, so why do it again? Let's just leave it as -5. So second time around is faster because we only have one determinant to find. So we have -4 plus 0 plus 3 minus 0 minus a -18 minus 12. And the bottom's -5. Add together the top. It's 5. The bottom's -5, so that's -1. So y is -1. Let's do the z. This time, the z column is the constants, and the X and Y columns are still the coefficients. The denominator is still negative 5 because it's just the determinant of the coefficients like X. So it looks like we get 6 plus 0 plus a negative 6 minus 0 minus 2 minus 3. Add those together, we get negative 5 over negative 5 is 1. So z is 1. So our answer is X, Y, Z. Another application of matrices is to find the area of a triangle given the vertices. Now, if you wanted to do this another way, you could graph them all, find the distance of the base, find the perpendicular distance to the other coordinate for the height, and go 1/2 base times height. That's real painful. This formula is much simpler. The plus and minus is simply so that you choose the plus or the minus to make the area positive. So let's find the area of the triangle with these vertices. So our area is plus and minus 1/2, and then the first point, 1, and then the second point, 1, and then the third point, 1. Let's use the shortcut to solve and find the determinant. So it looks like we get plus and minus 1/2, don't forget that's still there, negative 12 plus 5 plus negative 6 minus 20 minus 9 minus 2. Let's add all those together. I think we get negative 44. So half of 44 is 22, and we're going to choose the negative so that negative times negative is positive. Our area should be positive. If we can find the area of a triangle by using the determinant with those points, then, well, what if the area is 0? If the area is 0, then the points are on a straight line. So that is a way we can test to see if 3 points are collinear. We don't have the 1/2 because it equals 0. So 1/2 of 0 is still 0. But we can use that determinant. If, in fact, that determinant equals 0, the points are collinear. Oh, but wait, if it gives you points along a line, if we have 2 points and just let one of the points be xy, then xy would be any point along the line. So that would give you the equation of a line. So let's find the equation of a line passing through these 2 points. So we have x, y, 1, our first point 1, then our second point 1, and that equals 0. Well, let's move that 0 so we can find our determinant. So copy over the first 2 columns. So that's 9x plus 3y plus 2 minus 27 minus negative x minus negative 2y equals 0. Well, let's collect the x's. We have 9x, and that's plus 1 more, so that's 10x. Collect the y's. There's 3 y's. Plus 2 more y's would be 5y. And then the numbers is minus 25. These are all divisible by 5, so if I divide them all by 5, so both sides by 5, I'll get 2x plus y minus 5 equals 0. And there you go, standard form for the equation of a line. Another application of matrices is using ciphers. It's called the Hill cipher. To encode a message, we convert our message into numbers. Now, to make it more interesting, of course, you could let each letter be a different number, but I just did A is 1, B is 2, C is 3, just so it's easy to remember. A space would be 0 in my setup. Choose some sort of square encoding matrix. The bigger the matrix, the more complicated the result. Then you're going to group the message numbers into matrices of one row and the same number of columns as the encoding matrix. So if it's a 2 by 2 encoding matrix, you're going to group your numbers into 2s. If it's a 3 by 3 matrix, you group it into groups of 3. Then you multiply these letter matrices with the encoding matrix, and that gives you a list of numbers. That encoded matrix is just the list of numbers. To decode, just use the inverse of the encoding matrix and do the same thing. Just pretty much go backwards with the inverse of the encoding matrix. This is nice in that the result is different numbers for the same letter. So you might have E 2 or 3 times, but they're all different numbers, which is different and harder to break because often messages were broken by just what's the most common number. Oh, that must be an E because that's the most common letter in the English language or something like that. The bad thing is if you know part of the message, you can crack it by, let's say, if you know the first word, then you can use that to decode the encoding matrix, and then you can easily decode the rest of the message. Let's encode the word lunch using this matrix. Well, L is the 12th letter, U is the 21st letter, N is the 14th, C is the 3rd letter, H is the 8th letter. We're using a 2 by 2 matrix to encode, so we need groups of 2. Oh wait, 8 is by itself, so we'll just stick a space at the end, put a 0 at the end. Take your first pair and multiply it by the encoding matrix. Remember, we multiply a row with a column, so 12 times 1 plus 21 times 2, 12 times 0 plus 21 times negative 3, which gives 54, negative 63. Let's do the next pair, 14, 3. So 14 times 1 plus 3 times 2, 14 times 0 plus 3 times negative 3, which gives 20 and negative 9. Let's do the last pair. Eight times 1 plus 0 times 2, 8 times 0 plus 0 times negative 3, which gives 8 0. So encoded, this message is 54, negative 63, 20, negative 9, 8, and 0, and looks like gibberish. To decode it, you do the same thing, only now you use the inverse of the encoding matrix. You'd have to do the inverse of this matrix. So you'd multiply the 54, negative 63 by that inverse, and that would give you back 12 and 21 for the L and the U, and so on.